So we have a little bit more to cover talking about electric potential. And one of those things is we need to talk about finding field from the electric potential. And previously we talked about finding potential from field, which was an integration process. So it makes sense if you're going the other direction that you'd be finding a derivative. And you can see we're gonna just start with something simple like the potential for a point charge and take the derivative of it. And once you do that, you work your way through the calculus and end up with the idea that the electric field is the derivative of the potential with respect to the radius. And it's gonna go from high potential to low potential. And so here's a real simple example. There's another example in your book where they uh, have some other variables in it, but just real simply, you start off with a function that is with respect to the x direction and want to find out what the magnitude and direction of the field are if the potential in this case is 6x squared minus 5x. And so you take the derivative of that function with respect to x, since that's the only variable in there, and then once you get that derivative, you evaluate it at 3 meters, since that's what it asked for, and end up with, in this case, a negative 31 I volts per meter. Now, if you had Y and Z as part of this, you would go through and find the field at X, the field for Y, and the field for Z, and then sum them all up. You'd leave them in their vector format, I hat, J hat, and K hat, and then you'd have your answer in. So now, one of the things we need to really talk about is the idea of equipotential lines. And so equipotential lines are just lines that represent surfaces where the potential or voltage is equivalent. So in the drawing that's on here, the red arrows represent the field out of a charge, and those dashed lines represent everywhere that the voltage is equivalent. So like the center line, the voltage might be 4 volts, and then the next one might be 2 volts, and the next one might be 1 volt. It's always decreasing as it goes away from the charge. It also represents areas where no work is done. So you can go around and around following a single line and never do any work. Or you can hop up and down and around from line to line. And if you end up where you started with your charge, then you also have done no work, which is very similar to mechanics. Should be a familiar idea. Last piece that's important is when you're drawing them, they're always perpendicular to the field lines. So if you know where the field lines are, you can draw the equipotential lines. They don't cross each other. They just cross the field lines at a 90-degree angle. And so you have a mathematical problem here where you're given a large plate that has a charge density of 3 times 10 to the minus 9 coulombs per meter squared. And the question is, how far from the plate is the potential 4 volts? And divided by epsilon naught, remember that's the field close to a large conductor. And then use volts is equal to the field times the distance. You could start with the integration of volts is E dot dl, but in this case it'll simplify down to ED. And then that distance ends up being just a little over a centimeter when you plug everything in. Well, I hope this gets you a good start. We'll finish up the chapter with this and move on to the next one. Bye-bye.